In our Spectroscopy 101 video, the purpose of this video is to provide you with an introduction to spectroscopy. Specifically, how spectroscopy can assist with identification of unknown luminous objects. This video is intended for a general public audience. Let's watch and learn. You've seen this before, a light moving in the night sky. What could it be? You know, it's hard to get photographs or video that show shape of an object at night. How can you get information about what that moving light is? Well, one way is to gather information called spectra. Spectra of luminous objects are the optical emission or reflection signature of those objects and contain large amounts of information about the atoms and molecules that are responsible for what we see. Let's look at several man-made lamps. First, incandescent. Here we have an airplane with 3 incandescent lamps. You can see the spectra on the right, which is a continuous band of light from the blue to the green, yellow, and red. There are other types of lamps. A heat lamp. Notice that it's also a continuous band of emission of light. However, it's concentrated in the red, and yes, near infrared that we can't see here, with virtually no blue. The energy of the light, the energy of the source producing the light, corresponds to the color. Blue is higher energy, red is lower energy. At any given energy, there can be a change in the level of intensity or brightness at any one color. A heat lamp has lower energy than these incandescent lamps. There's a color temperature that you'll see when you purchase lamps in a store. Now we see a fluorescent lamp. And instead of just the continuous band of energy, we now see concentrated zones in the blue and the green and the yellow. These correspond to the atomic element mercury, which is an important part of the operation of a fluorescent lamp. The mercury is a volatile metal and helps to assist with the starting. Here we see an actual mercury vapor lamp. These are the bluish-white lamps you can see at night along the street. And indeed, it contains discrete individual lines of emission that correspond to the excitation of the atoms as a result of the energy that's put into the lamp to make it emit light. Violet, blue, green, yellow, and orange. It turns out that orange is not really from mercury. It actually comes from sodium. Sodium is present everywhere as a contaminant, as well as intentional, as in this sodium vapor lamp. These are the orangish yellow lamps that you see also at night lining the streets and on buildings. You can see the mercury lines that are present because that's important for the starting of these lamps. But the brightest feature is that incredibly intense yellow color, which is the same color you would see from a candle or from lighting a match. Sodium. Finally, we have not a man-made lamp, but instead nature, a lightning strike. Notice that it doesn't contain hardly any red. The only sodium that's there is what's incidentally present in the atmosphere. Instead, we see the incredible, strong, high-energy, bluish-white color of a lightning strike. In summary, spectroscopy can help us understand the origin and nature and chemistry of what is emitting the light and help us understand that object that we see at night. How do we obtain a spectrum if it's so useful for understanding the chemistry of an object that emits and reflects light? Well, here you see the familiar compact disc. There's ceiling lamps, a series of them, illuminating it from the upper right. All it takes is a regular array of lines or particles or dots spaced very close together to break a beam of light into multiple segmented paths that will interfere with each other constructively or destructively, similar to waves on a pond if you throw many rocks in at the same time. This interference pattern causes light of particular wavelengths to appear at particular positions offset from the reflection or transmission of the main beam. It turns out that for the case of diffracted light, the bluest wavelengths are closest to the main reflection and the reddest are farthest away, with green and yellow in between. Materials with such regular patterned arrays are called diffraction gratings, and this CD can act as a diffraction grating. Here we have a recently developed high-tech spectrograph that contains 2 diffraction gratings in a unique, patented configuration that allows us to obtain very precise information about the chemistry of luminous objects, and not just one at a time, but many at once, and even if in motion. Let's take a look. We're going to take a look at that fluorescent lamp through this high-tech spectrograph, And indeed, we see a much more detailed spectrum than what we saw before. That single yellow line is now split into two. They're only 2 nanometers apart. This is extremely high resolution from such a small device. You may notice too that this lamp is flickering. The plasma gas within the lamp is not stable. The mercury lines are, but the gas is not. Here we have a spectrograph you can build yourself by stripping the reflective coating from a CDR compact disc, cutting it to size, and taping it over the camera lens of your phone. You'll be amazed at what you can see. Rainbows everywhere, and based on the rainbow you see, you can identify the chemistry of the lamp that produces the light. So take the cell phone with a diffraction grating in place from the compact disc and look at what you can see. All the lights that we discussed earlier: mercury vapor, sodium vapor, there's an additional one here, metal halide, incandescence, there's some LED lamps, sodium vapor. You can identify all of those lights in the night sky and understand the chemistry and origin. Interestingly, we have here what appears to be a mercury vapor lamp from the mercury lines and from the blue color. However, you'll see the colors shift. This spectrograph that you've developed, that you can place on your own phone, will allow you to see multiple objects at the same time and in motion and changing in real time in front of your eyes. Here, as the lamp warms up, it's a sodium vapor lamp. Sodium is now being vaporized and energized to produce its characteristic spectrum in the yellow. So the lamp shifts color from blue to yellow to orange as it warms up. In addition, a car is going to show up in the parking lot here in just a moment, and you'll see its incandescent headlamps appear to the right-hand side. That'll be a very strong contrast of that continuous band of optical emission from blue to yellow to red, and here it comes now, compared to the sodium vapor next to it from the lamp. So here we have the power of being able to identify the chemistry and understand what that moving object is. This is a much more complex scene where we're going to look at airplanes and cars all in motion. In this case, the spectrum is turned on its side so it can better fill the screen. And you could probably now identify for yourself the different types of lamps. Here we have the incandescent, both on the airplane and on the cars. However, some of these cars are going to have lamps with the line type spectrum, where the atomic elements are present, such as the sodium and the mercury. You can also see the street lamps, and you can see everything happening in motion, even in different directions. This is an example of the spectrograph design that's being implemented in our station, whether it is a transmission type grating placed in front of a camera, like the cell phone, or whether it is this special patented high-tech spectrograph, as you see here. Our plan is to be able to deploy these devices to be able to look at the sky, identify the lights, and understand their chemistry and origin.
We introduced you to the equipment and results that can allow for the identification of unknown luminous objects. There is more that we plan to accomplish with this valuable equipment. Spectra can show us not just the chemistry and possible origin of an object, but also the physics of the object. Let's take a look. In our first video, we briefly mentioned that color equals energy, blue having more energy than red. Well, from the color of the peak intensity, we can measure the temperature of the object. This is like having a remote thermometer. In our first video, we compared light sources that have line-type spectra with those that have a continuous band of light. Well, if lines are present, we can study them not just for the atoms and molecules that create the light, but also at least 3 very important physical measurements: magnetic fields, pressure, and velocity relative to us. Magnetic fields present at an object's source of light can cause some lines in a spectrum to split into more lines. And we can remotely measure the strength of that magnetic field at the object using this technique of spectroscopy. We saw in our first video a sodium vapor lamp warm up. As the pressure of the sodium increases with the lamp's warm up, The yellow sodium lines broaden with increasing pressure, and this can be measured remotely by spectroscopy. You may have heard about Doppler shift. This is how astronomers know if objects are moving toward us or away from us. This is also how astronomers measure the rotational speed of galaxies. So, in the cases where the light that produces a line spectrum moves at extremely high velocity, we can potentially measure its speed relative to us based on the Doppler shift of the lines. This is a slight color shift that a high-resolution spectrograph can measure, such as the Echelle spectrograph mentioned in our first video. A shift to the red means the object is moving away from us, and to the blue means that it's moving toward us. All of these physical properties can be measured as they vary with time. So, if the lights are pulsing, or if the magnetic field or pressure is changing, or if there is a rapid change of direction of motion, spectroscopy can tell us remotely that this has happened. To complete this video, let's take a look at some example spectra that have already been obtained by one of our research consultants, Dr. Massimo Teodorani, for luminous objects that cannot be classified as known man-made or even known natural phenomena. When this occurs and we record and document it, as shown here, we have the chance to learn something new about the universe and the world around us. It is truly remarkable that many in the field of science today seem to want to shut their eyes to the possibility that there is some new physics or chemistry or even other life origin that exists which just doesn't fit our comfortable view of the world and the universe around us. So, this is why the UFODATA project was chartered. We greatly appreciate your time in viewing our video and visiting our website. Look for new updates regularly. We certainly appreciate your interest in the work that we are doing, and we appreciate your involvement to help us advance an area of science that is greatly neglected today. Thank you.